In this video, we're going over the concepts of chapter 7, which is titled, What's the Attraction? When we're talking about attraction in chemistry, we refer to attractive forces. And overall, in section 7.1, we are going to view two types of attractive forces. This table is representing the two types of major classes of attractive forces that you need to be familiar with. The first one is the type of force that exists between atoms, and that is known as intramolecular forces. Since this is the force that is in between atoms, it actually refers to the different types of bonds that we have in molecules in chemistry. You can observe that we have ionic bonds and we have covalent bonds. Out of the two, ionic bonds are going to be stronger than covalent bonds. In previous chapters, we already referred to what are the combination of elements that produce ionic bonds versus covalent bonds. But just as a quick reminder, many ionic bonds are formed by combining a metal with a non-metal. This non-metal can come from groups 5A, 6A, 7A from the periodic table, or sometimes we can have polyatomic ions. When it comes to the metals, remember that the metals can come from specifically the different types of metals that we have in the periodic table, like group 1A, 2A, the transition metals, so on and so forth. So please make sure that you review what are the type of components that when they come together, they make an ionic bond. In the case of covalent bonds, these are going to be made by compounds that are made from two or more non-metals coming together in a chemical formula. In addition to intramolecular forces, we also have what are called intermolecular forces. And intermolecular forces are going to be the forces that exist between molecules. So for the most part, intermolecular forces, we're going to look at two different compounds or two different molecules, even if it's a molecule interacting with another molecule of itself. We are defining what kind of forces are actually present between those two molecules. When it comes to the different types of intermolecular forces, understand that we're going to have three different forces that you need to be familiar with. The first one is going to be dispersion forces. And when we compare it to the other two, dispersion forces are actually the weakest. Dispersion forces are found in every molecule. Because as long as a molecule has electrons, dispersion forces are going to be present. So what are dispersion forces? Dispersion forces essentially are going to be forces that are going to come as a result of temporary dipoles. These temporary dipoles come from the idea that electrons in an atom or in a molecule are going to be moving around, and temporarily they're going to create two poles. That's why we have the word dipole, meaning two poles. What are the two poles that are created? One positive, one negative. Now notice that we're using the symbol delta because these are not full charges. These are partial charges. So once those partial charges, in this case, temporary charges, have been created, understand that the dispersion force actually results from the interaction of the partial negative and partial positive of neighboring molecules. So the dotted line that we have here is what's representing the dispersion force. A force that is present in molecules that have a permanent dipole, like polar molecules, those forces are called dipole-dipole attractions. And here we are representing that this dipole-dipole attraction we're going to have in a system that it is covalent. And we can observe that X and Y are going to represent nonmetals. Now, the difference between the molecule that we see on the dipole-dipole example versus the dispersion forces example is that in dipole-dipole attraction between molecules, these are going to be permanent dipoles because the molecule has polar bonds. Or overall, the molecule is polar. So here we have illustrated a dipole-dipole attraction, which is happening between two molecules of bromine monochloride. As you can observe, the dipole-dipole attraction is going to be between the partial negative charge of one molecule to the partial positive side. Now, these partial charges come from the electronegativity difference between the two atoms, but it is important to note that in order for having dipole-dipole attractions, the molecule needs to have polar bonds or the molecule needs to be polar. Lastly, we have hydrogen bond. And hydrogen bond is going to be the strongest out of the attractive forces that we have here. Hydrogen bond is what is called a quote-unquote hyper dipole-dipole. And in this hyper dipole-dipole state, what happens is that the molecule needs to have a polar bond, but this polar bond is very specific. In order for a molecule to have hydrogen bonding, that polar bond must be when hydrogen is connected to an electronegative element like fluorine, oxygen, or nitrogen. So whenever we think about hydrogen bonding, we always think that the hydrogen atom must be quote unquote connected to a fun element. The fun element is FON, and it refers to the elements fluorine, oxygen, and nitrogen. As we can see in the example, here we have the molecule hydrogen monofluoride, and we can observe that the hydrogen bonding event, it is occurring between the electronegative fluorine in the molecule and the electropositive hydrogen in the neighboring atom. So all of these attractive forces in common has the idea of having either temporary dipoles, like in the case of dispersions, or permanent dipoles in the case of dipole-dipole attractions and hydrogen bonds, but it's always that connectivity and that attractive force that is happening in between those partial charges that are partial negative and partial positive. Now, how do we determine the attractive force in a molecule? Here in this flow chart, it can actually help you determine what are going to be the attractive forces in a particular molecule. Let's say that we have, for example, the following molecules. Let's say that we have NaCl. Let's say that we have carbon tetrachloride, just to use these two examples. Let's first use the example of NaCl in order for us to understand how to utilize the flowchart. So for the start of the flowchart, we start with this initial question. Interacting molecules or ions. And then in the case of NaCl, you have to ask yourself, are ions involved? Well, in sodium chloride, sodium is a metal, chlorine is a non-metal. So ideally, how that compound actually looks like is in the following manner. Na plus, Cl minus. Since our compound has ions, then we have to say yes. Then it says, are polar molecules and ions both present? Then you have to say no, because here I'm just looking at the attractive forces in specifically just sodium chloride. So because of that, then this leads me to understand that specifically ionic bonding is going to be the main attractive force for when I have sodium chloride interacting with itself. Let's look at the example of carbon tetrachloride. In the case of carbon tetrachloride, we have to ask ourselves, the interacting molecules or ions? Are ions involved? The answer is no. Then it asks you, are molecules, are polar molecules involved? Carbon tetrachloride is not a polar molecule, so we have to go towards here. And as you can see, this leads us to understand that in carbon tetrachloride, what is present is London forces. And London forces is another word that can be utilized for dispersion forces. For looking at the polarity of carbon tetrachloride, I just want to remind you that the best way to determine its polarity, even though we know it is nonpolar, is by looking at the Lewis structure for the molecule. And since the Lewis structure for the molecule represents a tetrahedral carbon that has 4 identical groups surrounding the central atom, that's why the molecule overall is nonpolar. So that's how I obtained those results. Now, just as a review, we understand that the matter that we encounter in everyday life is going to be classified in terms of their physical state. Even though there's 4 physical states, let's understand that for the purposes of this class, you guys are responsible for knowing the states of matter that are the most common with the substances that we have around us. And those include solids, liquids, and gases. What happens overall when it comes to this concept is that These three states of matter can be categorized depending on their shape, their volume, their arrangement of particles, the interaction between particles, and the movement of those particles. And we can see here that if you have some substance that is in solid, that solid is going to have a definite shape and a definite volume. The arrangement of those particles is going to be fixed and is going to be very close. The interaction between the particles is strong, and the movement of the particles is going to be slow. In the case of liquids, on the other hand, liquids take the shape of the container. They have a definite volume. The arrangement of the particles is random. They are actually arranged close to one another. The interaction is strong, but the movement of the particles is actually moderate. Lastly, when it comes to a gas, gases take the shape of the container and they actually fill the volume of the container. The arrangement of those gas molecules is going to be random and is going to be far apart. And the interaction between the particles is actually essentially none. And those molecules are going to be moving very fast. So the reason why we talk about the state of matter is because the attractive forces have to do with how these molecules are going to change into other states of matter, okay? So as you can see in section 7.2, liquids and solids, specifically, those substances are going to have specific attractive forces, but I want you guys to be familiar with how attractive forces between two compounds are going to allow them to move. As you can see in the first bullet point, attractive forces are stronger between two compounds that are moving slowly. If we have a substance that is heated, then the particles, molecules, ions, whatever is present in the compound or the substance forms these attractive forces from the beginning, and then these molecules are going to move quickly and the attractive forces will become less important overall. So it is important that overall we understand the different changes of state that are going to happen between solids, liquids, and gas. As a summary, the image that we have on the right side of the slide tells you what are the differences between, or what are the changes when we change from solid, liquid, and gas, and the specific terms that defines them. So if we have a solid changing into a liquid, that is known as melting. If we have a liquid forming a gas, that is called boiling. If a gas is forming a solid, that is known as deposition. Now, let's see how these processes can be changed overall from solid to gas to liquid back to solid. So if a solid changes to a gas, that process is called sublimation. If a gas changes to a liquid, that is known condensation. If a liquid is changing to a solid, that is called freezing. The main thing here is that you need to know that all these changes of state happen due to changes in temperature. And upon the different changes of state, since those particles, molecules, and ions are going to move quickly, the attractive forces overall, when these changes are occurring, are not going to be as important as when the system is interacting with itself in one state. It is important to note that attractive forces also have to do with solubility. And in chapter 8, we are going to look at solubility in more detail. But at least to give you an introduction of attractive forces and solubility, let's understand that in chemistry, we have a rule of thumb. That rule of thumb is that, quote unquote, like dissolves like. What that means in terms of the molecules that we are going to be encountering is that polar molecules, if you need to dissolve them, you need to dissolve them in polar solvents. So we can see that overall, if you have a polar molecule, a polar solvent needs to be selected because the attractive forces that are found between the molecules are going to be allowing them in order to make a homogeneous mixture. The three types of attractive forces that can be observed when polar molecules are dissolved in polar solvents include ion-dipole attractions, H-bond attractions, and dipole-dipole attractions between two molecules. When it comes to the case of nonpolar molecules, understand that they will dissolve in nonpolar solvents. And here we have some examples of nonpolar solvents, which include hexane, toluene, and carbon tetrachloride. So if you have two substances that are nonpolar, then understand that the main attractive force that is going to allow them to combine and make a homogeneous mixture or will allow them to dissolve is going to be dispersion forces. And that comes from the idea that in dispersion forces, that is the strongest attractive force that is present in the molecule. Now, in chemistry, we also have some molecules that have that duality of having polar portions and non-polar portions. As you can see, if a molecule has both polar and non-polar parts, then there's going to be hydrophilic and hydrophobic competition in the molecule. What does this mean? If we take the following example, which is oleic acid. Oleic acid is a molecule that in this portion of the molecule is polar. And then the area that I'm highlighting in blue is actually non-polar. Overall, this molecule, because it has a large non-polar portion, is going to diminish that polar side of the molecule. So if we have to dissolve this substance in or combined with another substance in order to dissolve them, understand that this molecule can dissolve only in non-polar solvents and it comes from the idea that looking overall at the molecule, the non-polar side of the molecule, or the non-polar character, is so large compared to the polar that it basically makes the molecule be overall non-polar. The hydrophilic and hydrophobic terms that you see written here have to do with how would this molecule interact with water. Now, let's establish that oleic acid is actually a compound that is found in oil. And by just common knowledge, if one would say that, Oil and water do not mix. So if something is afraid of water, then we call it hydrophobic. If something is in love with water, then we call it hydrophilic. Oleic acid, because of its composition, will it be afraid of water or in love with water? If you guess that overall oleic acid is afraid of water, you are correct. And again, the reason why it will be afraid of water and it will not combine with water or dissolve in water is because of that large nonpolar character that is following the C double bond O bonded to OH in the molecule. And that nonpolar character comes from those nonpolar bonds that are made from the carbons and hydrogens in the molecule.